Right here we're going to look at group 2. So group 2 of the periodic table, and they're called the alkaline earth metals. You would have studied group 1 at GCSE, and we'll call those alkaline metals. These are the alkaline earth metals. We'll call the group 1 the alkali metals because they form hydroxides which are alkaline. These also form hydroxides which are alkaline, so we'll call them alkali metals, and we're finding the earth, so we'll call them the alkali earth metals. So this is group 2 elements that form alkaline solution compounds. That's what they are. For example, e.g. calcium hydroxide solution is an alkaline solution. Remember, this has to be 2 OH minuses because the charge on the calcium is Ca2+, so I need 2 OH minuses to balance the charge. Don't forget there we're using brackets, so it's 2 times everything in that brackets. So the AQ, remember, means dissolved in water. So like group 1, these are S block elements, and they react in similar ways to group 1 actually, but they're a little bit less reactive, which makes sense because what we're trying to do here is we're trying to remove 2 electrons rather than 1. So group 1, we're removing 1 electron, and group 2, we're removing 2 electrons, and that's why the group 2 elements are slightly less reactive than group 1. So we're going to look at the physical properties of group 2 elements first. Now, if we look at group 2, beryllium, magnesium, calcium, strontium, barium, and radon. There are trends as you go down this group, but there's a few exceptions that you need to be aware of. So we're going to look at the electron arrangement first of all. So the electron arrangement of beryllium, if you work out the electron arrangement of beryllium, count the number of electrons in that particular atom. Beryllium has 4 electrons, so that's 1s2, 2s2. Magnesium, let's not write down the full electron arrangement. Let's take the previous noble gas. So that's neon, in square brackets, 3s2. Calcium is argon, 4s2. Strontium is krypton, 5s2. And barium is xeon, 6s2. And radon, after barium, it's not based on xeon, it's based on radon. So radium is radon, 7s2. So we can see here that we've all got an s2 subshell filled there. So there's an s orbital filled within this subshell. Go look at the size of the atoms now. So as you go down the group, the atoms get bigger. They get bigger because we have more shells as we go down that group. There's more shells, so the atoms get bigger. Melting points. So let's look at the melting points now. You only need to know the trend of melting points from magnesium to barium. So this is the melting point in Kelvin. Let's ignore this one for now. We can see here that the melting points decrease, going from calcium to strontium to barium. Let's look at the reason why melting points decrease. So we have a structure that contains calcium ions. Remember, each of these ions has 2 delocalized electrons. So let's compare calcium to something like barium. Now, barium has much bigger ions. So barium has much bigger ions than calcium. So barium ions are bigger. And because we have bigger ions, we have a lower charge density. If there's a lower charge density, there's a lower electrostatic attraction between the positive metal ions and the negative free delocalized electrons. So there's a lower electrostatic attraction between the positive metal ions and the negative free delocalized electrons. And that's because the ions are much bigger, so they have a lower charge density. So that force of attraction is going to be much less. If the force of attraction is going to be much less, it means less energy is needed to overcome that force of attraction. If less energy is needed to overcome this electrostatic force of attraction, then the melting point will be lower. So magnesium doesn't fit the trend, and that's because magnesium has a different structure. So magnesium does not fit the pattern as it has a different structure. But in general, the melting points decrease as you go down group 2. Okay, let's look at ionization energies now. Now the ionization energies are important. They're important because you need to remove these electrons for these elements to react. Now these elements always go from the atom to a 2+ ion by removing 2 electrons. So we're interested in the first ionization energy and the second ionization energy added together. So here are the values. So I'm going to write down the first one here, the second one here, and then the first one add the second one here. Remember, we need to remove 2 electrons from these ions to give them a full outer shell. And we should recall that ionization energies are measured in kilojoules per mole. So it requires 2,189 kilojoules of energy to remove 2 moles of electrons from an Mg atom. Okay, when I'm writing these out, you should notice a pattern. You should notice that the sum of the ionization energies decrease as you're going down the group. Why do they decrease as they're going down the group? They decrease going down the group because those electrons that you're trying to remove are further away from the nucleus and more shielded from the nucleus because there's more shells. So they decrease as the group is descended, as there are more shells and the electrons being removed are further away from the nucleus, so they get easier to remove. The shielding increases. So those electrons that you're trying to remove feel the force of attraction to the nucleus much less as they go down the group. That's why the ionization energies decrease. Okay, we've looked at the physical properties of group 2. We're now going to look at the chemical properties of group 2. This is basically how they react. So remember, oxidation is a loss of electrons. So all of these reactions in group 2 metals are oxidized. The metals go from oxidation state 0 to oxidation state +2. So these are all redox reactions. Let's give an example. So this is a half equation. So if I take an Mg atom, which is a group 2 element, I need to remove 2 electrons. Therefore it becomes Mg2+, and I do that by removing electrons. Remember, oil rig, oxidation is loss of electrons. So Mg is oxidized. You'll find that nearly all of these reactions, that's exactly what we're doing here. We're removing 2 electrons. That's why we were interested in the ionization energies, the first and the second added together, because we're removing 2 electrons. Right, let's look at the reaction with water. So with water, you see a trend in the reactivity. The metals get more reactive going down the group. Let's look at an example. So the common example, or the generic example, which can use M here. So M could stand for any group 2 element. Now they're all solids at room temperature. Water is a liquid. And we form metal hydroxides. And their solutions. And hydrogen gas. So you would observe bubbles. observe bubbles, and you would see that the metal would appear to dissolve away. And what it's doing is it's reacting with water. So you see bubbles of hydrogen gas which are produced, which you could use a lit splint to give a squeaky pop test, and it makes an alkaline solution. So an alkaline solution is something with a high pH. Okay, I'm going to look specifically at the reaction of magnesium with water. Now, magnesium is toward the top of group 2, therefore it reacts quite slowly with cold water. But it actually reacts rapidly with steam, and it produces a slightly different product. So let's have a look. So we expected here to make a hydroxide, but actually when you react magnesium with steam and not liquid water, so this is magnesium with steam and not liquid water, you don't get a hydroxide. I'll show you what you get. This is just with steam. Notice that steam here, I've used H2O gas instead of H2O liquid. So we do not get a hydroxide, we get the metal oxide instead. And again, we get hydrogen gas. Okay, now if we compare the reaction of calcium, the reaction with calcium reacts even more vigorously. And the reason why that is because calcium is more reactive than magnesium. And then if we compare strontium, strontium is even more reactive. And the last one is barium. So barium is more reactive still. A bit of a story with barium. So I took a job as a head of chemistry in a school. It was a while ago, and I found a little jar, and I couldn't really make out what the label said on this jar. And I got some tweezers, and I noticed this metal was covered in oil. So I immediately thought this is going to be a reactive metal, because we know that we use oil to stop metals in group 1 reacting with the oxygen in the atmosphere. So I originally thought it was a group 1 metal. So when I pulled out the bit of metal out the jar, I thought this is quite hard. It's got quite a high density, much higher than a group 1 element. And I made out on the label it said barium. So I thought, well, this could be interesting. What I would like to do is I would like to react barium with water. I want to see what it looked like. But the problem was the piece of barium that was in the jar was quite large, and I didn't want to use it all in one go because I wanted to practice the experiment before I did it with the students, because I only had one bit. So I thought, right, I need a way of cutting the barium. And I thought, well, I know that group 1 elements are really easy to cut. I remember that from GCSE, you can cut them actually with a knife. However, group 2 elements have got a much higher density. So you're unable to cut them with a knife. So I thought, right, I need a different way of cutting this. So I cleaned the oil off the piece of barium, and I tried knife, and it didn't work. So I thought, okay, there's an excellent design and technology department downstairs. So I went downstairs with the piece of barium, and I told the design technology technician, I said, is there any chance we can cut this piece of metal? Of course I didn't tell the design technology teacher or technician what the metal was. I thought that was totally irrelevant. So he gave me a hacksaw, and apparently hacksaws are really good for cutting metal. I didn't know this at the time, but apparently it was. So he said, just use that vise there, stick it in the vise and use this hacksaw and it'll cut the metal quite fine. So I stuck the bit of metal in the vise and I started sawing it. And it was one of those old-fashioned design technology benches made of wood. So I stuck it in the vise, in this wooden vise, on this wooden bench with a hacksaw, and you know that friction can be produced when you saw something, particularly when you saw metal. A lot of friction is produced, and I took one sort of swipe at it with a saw, and the whole thing exploded. So it exploded because obviously barium is very reactive, and I never got to react barium with water, so I've never seen it before. So because I took like the only piece of barium that I've ever had or ever seen, and I stuck it in a vise and it exploded. So if there's anyone out there who has reacted barium with water, then it'd be interesting to hear of that. So barium is the most reactive, and it reacts with water apparently, which I haven't seen. Okay, so what we're going to need to know now is we're going to need to know some uses. So the use of magnesium hydroxide. So magnesium hydroxide is used in indigestion remedies to neutralise excess stomach acid, which causes heartburn. So milk of magnesia, which is this stuff here, magnesium hydroxide, it's used in indigestion remedies to neutralise excess stomach acid. That causes heartburn. Let's have a look at actually how that does that. So if you've got some excess stomach acid, which is hydrochloric acid, what you might take is, you might take some milk of magnesia, and the milk of magnesia will neutralise this acid. It'll neutralise the acid to make magnesium chloride, and whenever you have a neutralisation reaction, you make water. Now we need to balance this equation here. So we've got two oxygens here, only one on here. Let's put a big 2 there, like that. And we've got 2 chlorines here, so we need a 2 there. Let's just check the hydrogens are balanced as well. 2 hydrogens there and 2 there, that's 4. And then 2 times 2, that's 4 here. So this is what's happening here. So you have your stomach acid, which is neutralised by milk of magnesia. Another important use that you need to know about is calcium hydroxide. Now, calcium hydroxide is sometimes called slake lime. So its everyday name is called slake lime. So I'm from a farming background, and I know that you put what we call lime on a field. So you might hear a farmer say, I'm spreading lime. And what the lime is used to do, it's used to treat acidic soil. So the majority of plants have like an optimum level of acidity or alkalinity in which to grow the best. Grass, for example, prefers a pH of around 6. So it likes it slightly acidic, but not too acidic. So if it's too acidic, the farmer might put slake lime on there to neutralise some of that. Other crops such as wheat, corn, oats and barley, they prefer a pH 7. So you definitely might put slake lime on a field if you were to test the pH of a field and the pH came out at, let's say, pH 5 or 5.5, then you might put some slake lime on the field to neutralise the acidic soil. So let's imagine that the acid is hydrochloric acid. see here the equation is very similar to milk and magnesia used as an indigestion remedy. Magnesium is actually used for the extraction of titanium as well. Okay, now most metals are extracted from the ores like this. You would take a metal oxide and you would react it with carbon to make the metal and carbon dioxide. The reason why you would pick the carbon is twofold. The first reason is that carbon is more reactive than the metal in the metal oxide. So we pick carbon particularly if the metal is less reactive than the carbon. So the carbon is able to displace the metal from the metal oxide, leaving the metal and carbon dioxide. For example, if this was iron oxide, you could extract the iron from the iron oxide using carbon. And that's because the iron is less reactive than carbon. So that's a common technique that we would use. Now, we could technically use the same technique for titanium oxide. So in theory this works. Because the carbon is more reactive than the titanium. So like iron oxide, titanium oxide would theoretically work using this particular method. However, what we find that any carbon which is left over in the reaction will end up reacting with the titanium produced. And you get something called titanium carbide. So titanium carbide is when titanium reacts with carbon to make this compound here, TiC, titanium carbide. Now the problem with titanium carbide is that it makes it brittle, which is no good, okay? So if you're trying to make a false hip for somebody, false hips often contain a high percentage of titanium. You can't extract the titanium using this particular method here. You can't do that because the carbon is going to react with titanium to produce titanium carbide, and that's going to be brittle and the structure will fall apart. So we need to use a different method. Okay, now if this method was viable, if it was, titanium would be really, really cheap because actually there's a high percentage of titanium oxide in the Earth's crust. So it would be a really, really cheap metal, but we find that titanium objects are not cheap. And it's not because the titanium is not readily available, because it is. It's because the process to extract titanium is quite complex. It requires a lot of energy and some expensive materials as well. So we're going to look at that process now. So it's a multi-step process. So the first step is where the titanium oxide reacts with chlorine. So it reacts with chlorine and what we call coke, which is just basically carbon. Titanium oxide out of the ground reacts with chlorine and carbon. And what that does is it produces titanium chloride, which is TiCl4, and carbon monoxide. So we need to balance this equation here. So we've got two oxygens here, so we need to double this. We've now got two carbons, so we need to put two here like that. We've got four chlorines here, so we need to put a big 2 there. So what we get is TiCl4 and 2CO. We then take the TiCl4 produced from the first reaction and we react that with magnesium. To make magnesium chloride and titanium. Let's put the state symbols in. That's actually a liquid. This is a solid. This is a solid. That's a solid there. And that's how we get with titanium, and that's quite pure. Unlike the titanium you produce in this method, which is contaminated with this brittle titanium carbide. Clearly this process here is going to be much more expensive than just simply doing this process here, because carbon is very cheap. Chlorine isn't cheap, magnesium isn't cheap, and the separation techniques which are going on here are not cheap either, which makes it titanium much more expensive than expected. Even though the original titanium oxide, the ore, is quite common. Okay, we're now going to look at the solubilities of the group 2 hydroxides and the solubilities of the group 2 sulfates. So, solubilities of the group 2 hydroxides. The trend there is that as they go down the group, they get more soluble. So they get more soluble as they go down the group. So if I pick a group 2 hydroxide at the top of the group, we would expect that to be almost insoluble. So magnesium is quite close to the top of the group, and that is almost insoluble. And so we can link that fact there back to the use of magnesium hydroxide. We know that the use of magnesium hydroxide is milk of magnesia. Now, milk of magnesia, if you buy it in the shop, it usually comes in a blue bottle. It's actually what we call a suspension. A suspension is when the solid particles in there are a precipitate and they're not all dissolved. So they're not all dissolved. So it's sold as suspension. So it's almost soluble, and milk of magnesia is sold as a suspension rather than a solution. So milk of magnesia is sold as a suspension rather than a solution. If you go down the group there, let's go to the next hydroxide, calcium hydroxide. We know that calcium hydroxide is slaked lime. This is the compound that a farmer might put on his fields to neutralise acidic soil. Now that is what we call sparingly soluble. So it's sparingly soluble, so it does require a little bit of rain for that calcium hydroxide to be dissolved in the soil. We don't want it too soluble, because if it was too soluble and it rained, all the calcium hydroxide would just run off into the river system and it wouldn't actually stay in the soil itself. Strontium hydroxide is more soluble still. And barium hydroxide is the most soluble. If something is more soluble, what happens is the ions in the ionic compound completely split up, they completely dissociate. Because they completely dissociate, they have lots of OH minus ions, which gives the barium hydroxide solution a very strong alkaline solution. Then we've got the sulfates. So we're going to look at the solubility of the sulfates of group 2. Now the solubility of the sulfates of group 2, it's exactly the opposite. It's exactly the opposite trend. So whereas the solubility of the hydroxides, they got more soluble as you go down the group, the sulfates get less soluble as you go down the group. So if we pick something at the very bottom of group 2, a sulfate at the very bottom of group 2, so barium sulfate is at the very bottom of group 2. And we know that they get less soluble as you go down the group. Barium sulfate is nearly completely insoluble. I've made a mistake there. Have you noticed here? I've put a 2 here after the square brackets. I don't do that. I did in this case here because we have OH minus. This is actually an SO4 2 minus. So it's 2 minus. I only need one 2 minus ion to balance the charge on a Ba2 plus. So that's not the chemical formula. The chemical formula of barium sulfate is BaSO4. And that's going to be a solid because it's insoluble. Now that's just as well, because barium sulfate is actually used as what we call a barium meal. So its use is in what we call a barium meal. It's not a takeaway option or anything. A barium meal is basically something that you would take when you're going to go into hospital and you're going to have a medical x-ray of your gut or your stomach. So what you would do is you would take a barium meal, you'd actually drink it, and then you would have an x-ray and the barium would show up in the x-ray. And the reason why the barium would show up in the x-ray is because the barium atoms are quite big, and what they would do is they would absorb the x-rays. So barium meal is taken in a hospital to outline the gut. And this is because the heavy barium atoms are very good at absorbing X-rays. Of course, your gut and your stomach wouldn't necessarily absorb a high percentage of X-rays normally. It'd only be things like bones that would do that. However, if you take a barium meal, it's the barium atoms within that absorb the X-rays. There is a fact here though that barium is actually highly toxic. However, this is still completely safe. The reason why it's safe is due to the fact that it's completely insoluble. So it doesn't really matter that the barium is highly toxic because it actually goes straight through your body. You would ingest it, so you take it in by mouth, and then it would go straight through you without actually absorbing into your bloodstream because it's very insoluble. So it's still completely safe, and that's because barium sulfate is completely insoluble rather. So it's not absorbed into the bloodstream. The barium sulfate, again, is got another particular use. It's actually used as a chemical test. So it's used as a chemical test for sulfate ions. So what we do is we take some barium ions like this, and we can react them with something which contains sulfate ions. That could be anything which contains sulfate ions. And because the product is insoluble, the product is always going to be a solid. So it's a solid, or what we'll call a precipitate. And it's white. Yeah. So we use that as a test for sulfate ions. So we use the barium ions to test for sulfate ions. And we'll look at how you'd actually do that in practice in another lesson. That's Group 2 Chemistry.